Yeah, just a quick introduction to our speakers today. Thanks everyone for joining us again this morning for another water issues seminar. Um, the area of disinfection byproducts, I think, is really an interesting and area of growing concern again, not only here but elsewhere. And I think that's what you're going to hear today. It was, I think, back in the 70s that the EPA, I think you guys can correct me if I'm wrong, but identified 11 disinfection byproducts that are currently regulated. And at that point, it just kind of, after that, I think it was a matter of, problem solved and people kind of forgot about it. And here we are in 2024. I think that's the year we're in again. And we're looking at it again. And today we're going to hear our presenters talk about the investigation of NDMA, or nitrosamine, a very toxic, carcinogenic um, disinfection byproduct that is not currently regulated by the EPA and drinking water treatment plants, so far as I know. And they're going to be talking about the precursors that go into the formation of NDMA, and when they enter the chloramination of drinking water treatment, we get this disinfection byproduct being formed. And so I think this is just a really, really timely topic, and I'm really interested to hear what Bill Arnold and Ray Hozalaski and their graduate student, Jackie Lee, are going to tell us about their investigation into NDMA precursors in Minnesota rivers. With that, take it away, you guys. The floor is yours.
Okay, hopefully everybody can hear me. I should first say that Jackie's no longer our grad student. She actually graduated and defended her PhD, and she's now a postdoc at Georgia Tech. So congrats to Jackie. I also want to start by acknowledging the support for this project, or for this work. So we were first given a small grant from the Water Research Fund here at the University of Minnesota, which is largely sponsored by Bernie Bullard. Then we received a larger grant from the Environment and Natural Resources Trust Fund of the Minnesota Legislature, and we want to thank the ENTRF for that. And then finally, I'd like to thank Sandeep Berman and the Drinking Water Protection folks at the Minnesota Department of Health for also supporting an expansion of our activities in this area. So thanks to all those organizations. So I'd like to move on to the first slide. So we'll talk a little bit about chlorine and disinfection byproducts. So chlorine, we all know, is widely used around the world for disinfecting drinking water supplies. It's largely responsible for our improvements in longevity and health in the developed world. And so the main goal is to take chlorine, react it with pathogens in the water for dead, or maybe better termed, inactivated pathogens. So we really just want the pathogens to be unable to reproduce. And so probably inactivated is even a better term. Free chlorine consists primarily of hypochlorous acid and hypochlorite ion, normally introduced into water via chlorine gas, although it could be introduced as sodium or calcium hypochlorite salts. And free chlorine, we know, is very effective disinfectant. However, it's also highly reactive, and it can react with other constituents in the water, including dissolved organic matter, or DOM, to form a series of halogenated disinfection byproducts, all including chlorinated, brominated, and even iodinated DBPs. And we know that many of these DBPs, or some classes of them, including the chloroform and bromoform, which are trihalomethanes, and trichloroacetic acid, shown here, which is a HAA, or haloacetic acid, are regulated. There are hundreds and hundreds of other compounds that are formed that are not regulated. But so this is, we know that when you add halogens to organic compounds, they tend to become more toxic and carcinogenic. Chloramines, however, are much more stable, less reactive than free chlorine, and they tend to form less of these halogenated DBPs, which makes them advantageous because you can add chloramines to the water, even if it has high DOM, like we do here, for example, in the Mississippi River. And that disinfectant residual should be much more long-lasting than free chlorine and form much less of these DBPs that are regulated in particular. Chloramines consist of monochloramine, dichloramine, and trichloramine. Predominantly in tap water, it's monochloramine is the main form, although you usually do have a little bit of dichloramine around. And the chloramines are formed by reacting free chlorine with ammonia. And so depending on the ratio of ammonia to free chlorine, you get the distribution as mono, di, or tri. So more free chlorine, you get more di and tri relative to ammonia. So chloramines plus, I should say, so now we'll talk a little bit about chloramines and their byproducts. So not anything you add to water has usually, if you want to add to drinking water, has usually a beneficial effect, right? You're trying to improve the water quality, but there often and almost always are undesirable side effects. And that's true even for chloramines. So we said that we don't form a lot of the halogenated DBPs with chloramines. However, we can form a class of compounds called nitrosamines, which are known to be highly toxic and potentially carcinogenic. The main nitrosamine that forms is N-nitrosodimethylamine, or NDMA, and that'll be the focus of this presentation. Unlike the halogenated DBPs, the nitrosamine precursors tend to be more anthropogenic chemicals as opposed to DOM. NDMA is, as I said, the most widely detected nitrosamine in drinking water. It's highly toxic. It's known to be a human carcinogen. And as stated by Mark at the outset, it's not currently regulated in the United States. There are values out there to look to as potential regulatory concentrations. For example, the notification level in the state of California is 10 nanograms per liter. And the Minnesota Department of Health has issued a guidance value of 5 nanograms per liter. And nitrosamines form, as we said, by usually by taking di or tri, what am I trying to say? Oh, like for example, this is an example of formation of nitrosamines or NDMA. So you take a dimethylamine, right? So secondary amine, and you react with, in this case, dichloramine to form this adduct, this dimethylamine adduct, in the presence of oxygen that reacts to form this nitroso-dimethylamine compound. And so basically the precursors for NDMA include secondary, tertiary, and quaternary amines. So you see the tertiary amine on the far left of the compound ranitidine, which is better known as Zantac, right? So that is the antacid that's been actually removed from the market because it turned out it was contaminated with NDMA. And so ranitidine is known to react with really high yields, 90, 100% yields to form NDMA upon exposure to chloramines. There are many other types of compounds that contain secondary, tertiary, and quaternary amines that are used in industry and health, including agricultural chemicals, antibiotics, pesticides, and even water treatment polymers like polydadmac has a quaternary amine, as you can see in that schematic in the middle. So we look at potential precursor sources as being wide-ranging. So we have industrial sources, both domestic and industrial wastewater treatment operations, agricultural operations, and even runoff from stormwater or stormwater runoff from urban areas, and potentially even algal bloom. So there are potentially some naturally occurring amine compounds that could be reactive to form NDMA. And so I'll briefly talk about lime softening, and I'll hopefully explain why we're talking about lime softening, and it'll come up again and again in this talk. So we were considering the effects of lime softening because we wanted to look at how precursor levels or concentrations change through water treatment. It turns out that the Mississippi River is relatively hard water, about 180 to 200 milligrams per liter is calcium carbonate. Desirable concentration is about 80 or 90 milligrams per liter. So it's more than twice as hard as it's desirable. So both Minneapolis and St. Paul and St. Cloud, in fact, if we go further up north, practice lime softening at full scale to remove hardness, predominantly calcium and magnesium ions. And so the process is to add lime to increase the pH along with coagulants. So usually you're talking about pH of 11, 11.1. And through lime softening, we get massive removals of dissolved organic matter as well as hardness. So the way that we mimic softening is to use what's referred to as a jar test apparatus, where we add the lime, and in this case, if we're mimicking what St. Paul does, or in their treatment plant, we'd add the lime and alum, and we rapid mix briefly. Then we add iron, ferrochloride, and slow mix, so-called flocculation, to allow the flocks to form. And then we have a 30-minute settling period. We pull off the supernatant, and that is our lime softened water. All right, so what we did, a preliminary investigation where we sampled the upstream portion of the Mississippi, upstream of the Crow River. And then you see that's location A. Location B was in the Crow, and location C was downstream in the Mississippi River after the two rivers meet. And so we were told by Bernie Bullard, in fact, who used to be the director of Minneapolis and St. Paul St. Paul Regional Water Services and Minneapolis Water Treatment and Distribution Services. And Bernie suggested that the Crow might be a reasonable place to look for potential precursor problems. And so we did that. We sampled these three locations. And what we found is if we just applied what's referred to as the Uniform Formation Conditions test to evaluate the levels of NDMA precursors. And so I'll explain more about how this works in a couple of slides. But basically, we don't know what the NDMA precursors are. And so the only way to figure out how many of them or what the concentration is in the water is to add chloramines, look at how much NDMA forms, and then that tells us essentially the precursor level in the water. And so you look at these data, and it's not very remarkable. It suggests that all three locations are about the same, A, B, and C. However, if we took the softened water and we apply the Uniform Formation Conditions test, what we found is quite interesting and quite startling. In fact, if you look at location A, which is upstream of the confluence with the Crow, the levels were comparable, both pre and post softening, in terms of NDMA formation potential via the UFC test. However, at location B, which is in the Crow, the concentration went up eightfold, or almost an order of magnitude, so from 4 to 32. And then if we look at location C, which is after the two rivers blended, again, it was, in this case, roughly a 20-fold increase in concentration. So what these results told us was two things. One is that it looks like the Crow is a potentially important source of precursors to the Mississippi River upstream of both Minneapolis and St. Paul's water withdrawals. And two, lime softening, which is both employed by both Minneapolis and St. Paul, is likely to be an important part of the process in potentially increasing precursor levels. All right, so the objectives, that's the background. So the objectives of this research were to assess the spatial and temporal variability in NDMA precursors along the Crow River, which I mentioned just in that last slide. It looked like it was a potentially important source of precursors to the Mississippi River. The second objective was to evaluate levels of NDMA precursors along rivers in 4 watersheds with different land uses. So we wanted to investigate whether this is peculiar to the Crow or whether it might be important, say, in the Red River out west. So we looked at 4 different watersheds: Minnesota, the Red, the Crow, and the St. Louis. And then the third was to assess the effects of lime softening treatment on NDMA formation. So we did some more work in that area. And then Bill will come in and talk about how we did some non-target analysis to identify the main NDMA precursors and their sources, and also some work we did to assess the effectiveness of pre-oxidation treatment for precursor destruction. All right, so just a little bit of a methods overview before I get into the results. So as already talked about, we employed lime softening in this work, add alum, ferrochloride, and lime to pH 11.1. And then after we soften the water, we bring the pH back down to 8.5. We evaluate NDMA precursor concentrations using the Uniform Formation Conditions test, so-called UFC test. And that involves a modest or realistic chloramine dose at 5 milligrams per liter as Cl2, incubate for 3 days, and then we measure the NDMA that's formed. And then we also evaluated the organic matter in the water, looking at excitation emission matrices, and I'll talk a little bit about that. And then next click. So if we do EAMS, so you see this plot here is excitation wavelength on the y-axis, emission wavelength on the x-axis, and then the color indicates the intensity of the signal. And so what this does, it allows us to investigate sort of the composition of the organic matter in sort of rough terms. So in regions 1 and 2, that represents aromatic proteins. Region 3 is more fulvic acid-like materials. Region 4 is microbial byproducts, proteins, biopolymers, etc. And then region 5 is more the humic acid type materials. And I'll get into this more, the results and what they mean for this work a little bit later. Bill? And then the other thing we did was we evaluated just crude bulk parameters for organic matter, including UV254, UV absorbance at 254 nanometers, total organic carbon test for measuring total organic carbon concentration, organic carbon in the water. We also did some size exclusion chromatography to measure the size distribution of the organic matter. And then we did some looking at the effects of anthropogenic activities and land uses in the watershed. So we scoured databases to look at the number of feedlots and the amount of animals in the watersheds, upstream of our sampling locations, wastewater treatment plant discharges, both industrial and domestic, septic tanks, brownfields, forest land, open water, cropland, and so on. And so we tried to look at correlations between these various anthropogenic activities and land uses and NDMA precursor levels in the watershed. So again, how do we quantify NDMA precursors, just so that we're all very clear on how this was done? So you take your water sample, you buffer the pH to 8 using borate buffer, and add preformed chloramines at a dose of 5 milligrams per liter as Cl2, incubate for 3 days at room temperature, and then you measure the NDMA concentrations in the water at the end. So rarely, if we measure NDMA in the raw water, we would pretty much have non-detects. So NDMA is not present, at least not in substantial concentrations in the water itself. It's only formed when we add the chloramines to the water. So we're measuring the NDMA precursor concentrations indirectly using the UFC test. And at the end, we quench the chloramine residual, and then we extract using solid phase extraction and analyze using LC-MS-MS the NDMA concentration. All right, so first I'll talk about the Crow River sampling campaign, and we'll look at both the concentrations along the watershed and then also the dynamics, or how things change over time. So next click, Bill. So the Crow is comprised of two forks, the two main forks, the North Fork, the South Fork. Those merge to become the main stem of the Crow, and then they eventually meet the Mississippi River at the northern boundary of Hennepin County. So we sampled these locations, the upstream North Fork, the middle North Fork, the downstream North Fork, and then the down mid North Fork. So you see those all labeled there. And then in the South Fork, we sampled those 4 locations. And then in the Crow, we sampled so-called upstream Crow and downstream Crow. And then out into the Mississippi River, we sampled upstream of the Crow and downstream of the Crow in the Mississippi River. So a total 12 sites were sampled. We sampled roughly monthly for about a year plus. Next click. And then bi-monthly for the last, 4 months or so of the study. All right, so this is these are some of the results from the study. So these are so-called box and whisker plots. And so you can see that there's no real significant step function, big increase anywhere along the river. So we see, for example, in the North Fork, right, the purple bars on the far left, the concentrations are uniformly higher than in the South Fork. So the North Fork seems to be higher in terms of NDMA precursor levels than the South Fork. And you see that the levels are pretty constant from the UNF location to the DNF location. In the South Fork, we do see a gradual increase from the USF location to the DSF location, but not a startling jump that would suggest like there's a real hot spot, a real a location that says, this is our our silver bullet. This is the problem here. So again, modest increase, but no big jumps. And then the upstream and downstream Crows reflect a little bit higher levels, more like what's in the upper or the North Fork. And then in the Mississippi River, with some dilution, the levels usually are a bit lower than they are in the Crow. All right. And if we look at temporal variation, we do see some rather interesting periods where concentrations could be much higher, and then concentrations are lower. So, like for example, you can click once, Bill. This July sample had among the highest concentrations we'd observed. This is before softening, so these are raw water concentrations. And this was about 120 nanograms per liter. And if you recall, the levels, like the California level of concern was 10 nanogram per liter, and Minnesota's notification or health guidance value was 5. So these values are much, much higher than we're talking about in terms of notification level in California, for example, and our guidance value. And then we see this other increase in the winter. So a peak in January of 21. So it seemed to increase and then peak in January and then come back down in February. And then we saw a little peak later on in summer of 2021. And okay, so can we go back? Yeah. So what the data might suggest, if you look at the blue in the data in the background, that suggests, or that's the river discharge. And so there seemed to be a loose, but not a strong correlation, inverse correlation between river discharge. So when the river discharge is high, often the concentrations of NDME precursors are low. And then when the river discharge is low, the concentrations tend to be high, but that's not universally true. But it was, I'd say, a weak correlation between discharge, inverse correlation. Thanks, Bill. So now we also explored the effects of lime softening treatment. So for all these samples that I just talked about, those were raw water before softening. And then we also compared the effect, the NDMA formation via the UFC test after softening. And so the raw water are the upside down triangles in orange or red, and the blue circles represent the lime softened samples. And note that this is a log scale. So 2 represents 100 nanograms per liter, 3 represents 1,000 nanograms per liter. And so you can see that in some cases, there's a huge increase in the amount of precursors present, or at least measured in the water when we do lime softening. You can click, Bill. And so if we look at the percent increase in NDMA precursor levels, you see that the 0 is the line that's across the, and so if we're on that line, that means there was no increase after softening. If we're below that line, which are the yellow data points, that means that there was actually a decrease. But by and large, the bulk of the samples, the blue circles, represent an increase post-softening. And so you see it in some cases, there's 1,000% or a tenfold increase in concentration of precursors after lime softening. Okay, we move on. All right, so that concludes the part of the talk on the crow. So we talked about spatial and temporal variation and NDMA precursor concentrations in the crow. And I'll get to this in a conclusion slide at the end. But again, the main take homes are that there was modest or very little spatial variability in the precursor levels in the crow. The North Fork was a little bit higher in precursor concentration than the South Fork. And then there was some dramatic temporal variation as we observed. Okay, now what we decided to do was to go out and explore 4 different watersheds. So we looked at again, the Crow River, which we already talked about. We looked at the Red River on the western border with North Dakota. We looked at the St. Louis River up just north of Duluth, Minnesota, and then the Minnesota River. And you can see where they are, of course, on the map in the middle. And we did a sampling campaign from May to July of 2022. So we did essentially a snapshot. So we went out and we did essentially a run along the river usually in 1 or 2 days, collected the samples and came back and did our experiments back in the laboratory. So this represents essentially a snapshot in time. So, all right, so what did we observe? So if we go again back to the crow, you can see on this bar on the right bottom that's highlighted. So we have NDMA uniform formation conditions or NDMA precursor concentrations on the left axis, river discharge on the right, and then there are pairs of bars for each sampling location. So the bar on the left is the raw water, the solid bar, and the bar to its right represents the softened water. And so what we see here again is what we had already basically described, except we did a snapshot in the summer of 2022, where we don't see any major hotspots, right? So the levels along the Crow are pretty stable, maybe some little up and down, and by and large, the softened water has substantially higher levels of precursors than the raw water. If we look at the Minnesota River, again, it's sort of comparable, right? No major hotspots, pretty consistent levels from about 40 to 60, a little bit lower usually in the raw water than the softened water. But again, pretty substantial levels even in the Minnesota River. Next. If we look at the Red River, we actually do see a gradual increase from sampling location, like at the far upstream end, R1, and then it sort of increases to this location, R3, about 108 river miles downstream, and then it just becomes more or less constant over time, maybe decreases a little bit further downstream. But if we look at the St. Louis River, it's quite unique. So the levels are really, really modest, low, really at the low end of our, detection, 2-3 nanogram per liter, especially when the river's flowing through the really nice forested areas upstream. However, when we get into the Duluth metropolitan area, what we find is a big step increase in precursor levels for the post-softening samples. And so those are those gray hashed bars on the far right, so those 3 bars. So again, this suggests to us that forested, pristine, let's say, regions are not emitting much precursors, but when we get into an urbanized area, we see a big increase in at least the post-softening precursor levels. All right, so we wanted to evaluate the effects of land use, so we looked at all these land use indicators, did a lot of GIS work. Jackie spent a lot of time doing data analysis. And so what we found is that the precursor levels correlated quite strongly with the number of animal feedlots. You can see the correlation is 0.57, so 1 would be a perfect linear fit, and the p-value is quite low, so it's a significant correlation. If we look at the total weight of animals in these feedlots, again, an even stronger correlation, almost to 0.7, again, a very, very low p-value. And then if we look at domestic wastewater treatment plants and capacity of these wastewater treatment plants, we also see fairly strong correlations. Again, the overall strongest correlation was with the total weight of animals, with the domestic wastewater plants being slightly weaker, but still strong correlations. And if we look at things like land cover, urban land use and croplands were really minimal or modest importance for both raw and lime softened samples. And it turns out that forested and wetlands had negative correlations, meaning that they actually tend to have lower or reduce the precursor concentrations relative to other land uses. So in summary, the animal operations appear to be the most important in terms of these correlations. Domestic wastewater was next, and then cropland was a distant third. All right, if we look at dissolved organic matter indicators, we see that as the total fluorescence increases, and total fluorescence is a measure of the bulk amount of organic matter in the water. So as we have more and more organic matter in the water, we tend to have less and less NDMA UFC, as shown in that top panel. And if we look at various regions of that EAMS, as we talked about, right, so region 2 is aromatic proteins, and region 4 is microbial byproducts, proteins, and biopolymers. And you see positive correlations between NDMA UFC, or precursor concentrations, and region 2 and region 4. However, if we look at region 5, which is the humic acid-like materials, we see a strong negative correlation. So a rho value of minus 0.55 in that bottom right panel, and a strong, very, very low p-value. And so that's suggesting that the more organic matter we have in region 5 in our water sample, the less and less precursors will be measured or identified or formed after chloramination. All right, so one of the things that we wanted to explore was, why are we seeing this effect of softening? So why do precursor levels increase post-softening? Normally, for regulated DBPs like trihalomethanes and haloacetic acids, if you remove organic matter and then chlorinate, you tend to have dramatically reduced formation of disinfection byproducts. Yet for an NDMA and chloramination, we actually see increased formation of NDMA post-softening. And so this is sort of counterintuitive. I mean, we're removing organic matter, which could potentially react to form precursors, to form NDMA, and yet we have an increase in formation post-softening. And so we wanted to explore this a little bit more. And so we look at what softening does to DOM, and it's well known that softening and coagulation removes DOM. And as you can see here, if we measure the dissolved organic matter levels by UV absorbance at 254 nanometers, regardless of the river, we always see a decrease, especially in the St. Louis. It's a quite dramatic decrease. If we look at total organic carbon concentration, it's a bulk measure of the organic matter in the water. Again, consistently large decreases. Normally 50, 60% or more of the carbon is removed when we soften the water. And then if we look at total fluorescence, again, we see dramatic decreases in total fluorescence when we soften the water. Again, if we look at the character of the organic matter in the raw versus lime softened, we see that this region 5, we see quite a dramatic decrease in the amount of fluorescence in region 5 after softening. Click, Bill. And so you look at the percent removal in region 5, it's like 95% removal of region 5 material when we lime soften, and 87% removal in region 3. So region 5 is the humic acid-like material, and region 3 is the fulvic acid-like material. And we also see a shift in the size of the organic matter or molecular weight to lower molecular weight when we soften the water. So softening with coagulation tends to remove the larger, more UV absorbing, higher molecular weight, more aromatic materials. And that's pretty well known in the literature. Okay. All right, so now if we look back at what happens to NDMA precursor concentrations as measured by the UFC test, the Uniform Formation Conditions test, for all these different water sources, the St. Louis, the Red, the Crow, and the Minnesota River, when we soften the water, we see an increase in NDMA UFC. So if we look at the blue, which is the raw water, versus the red box and whisker plot, we always see an increase from blue to red for all these waters. And again, that's telling us the same thing. Softening tends to increase precursor levels in almost all cases. One thing that we decided to do experimentally was to put the organic matter back in the water. So for example, if we took like raw water, if we compare the solid bar and the blue bar with R, so that's the raw water, and then we compare it to the LS, the orange bar on the far left and the plot on the right, we see that for the raw it was around 22 nanogram per liter, and then for the lime softened, it's around 27, 28. So a modest increase, but maybe 20% increase in precursor levels after softening. However, let's focus on the orange bars on the right. If we took that lime softened water and then we added back the organic matter in the water, so we actually took organic matter and dosed it back into the water, you see that the amount of precursors that formed decreased with each increase or incremental increase in the amount of organic matter in the water. So what this is suggesting to us is that by adding more organic matter, we are somehow either protecting the precursors from reaction with the chloramines, or the chloramines are reacting with these organic compounds, the organic matter in the water, and not with the precursors. So essentially there's a competition between the natural organic matter and the precursors for available chloramines. And so we wanted to explore these things a little bit more, so we can move on. So we looked at some models that were available in the literature to try to predict NDMA formation. And so this top equation where P is the precursor. In this case, our model precursor was this Zantac or ranitidine, which is the molecule shown at the bottom. And so if we look at how precursor reacts with monochloramine and then or dichloramine, so we can essentially look at the disappearance of the precursor by reactions with mono and dichloramine to get an overall disappearance rate. And then if we know the conversion of precursors to NDMA, which is the theta value shown there, if we multiply theta by the loss or the change in precursor concentration, then we can obtain an estimate of the NDMA that should have been formed. And so theta for ranitidine is like 0.9 or 1. So it's virtually a 1-to-1 or 100% conversion. And so what the modeling told us is that if we vary the TOC concentration, which essentially is mimicking the effects of softening. So if we look at the dashed is the TOC, let's say before softening, 6 milligrams per liter. And then the solid line represents the TOC after softening, let's say 2 milligrams per liter. Then what this tells us is that the concentration of chloramine, the orange line, would be lower when the TOC is higher. And if we look at the blue lines, the solid blue line is when the TOC is low. We get more NDMA formed than when the TOC is lower, the dashed line. So the blue lines are the chloramine, or the NDMA, and the orange lines represent the monochloramine concentration. Next. And then we looked at two different models available in the literature. And this other model showed a much more dramatic effect on the chloramine concentrations that would form. So again, if we focus on the blue lines, those are the monochloramine formation over time. And the solid blue line is for the low TOC case, and the dashed line is for the high TOC case. And you can see, for the high TOC case, it's like 20 nanogram per liter, and for the low TOC case, it'd be 160. And so what these model results tell us overall is that if we soften the water and remove organic matter, then we have less competition for chloramines with the precursors. And so the precursors are tending to get more of that chloramine that's available, and they can react to form NDMA. All right, so this is the proposed mechanism. So if we take a model precursor like dimethylamine, for example, and we know that dimethylamine has a pK of 10.7, so below that pH, the dimethylamine should be positively charged, as you can see there, the pink. So click, Bill. And so in the water, we would expect, you can go ahead. Yep. That the dichloramine is, as a positively charged molecule, it would react with the negatively charged NOM and potentially be sequestered or enveloped by this negatively charged organic matter, as you can see in this plot. So we maybe have some free dimethylamine and some that's bound or interacting with the NOM. And that would be in the raw water. And so you can imagine now if you add monochloramine to the water, next click, the monochloramine is going to react partly with the NOM and partly with the dimethylamine, and then you might get some formation of NDMA. However, if we look at lime softening process where we have pH of 11.1, now our dimethylamine is neutral, right? So it's no longer positively charged. So it's less likely to be reacting or interacting with the organic matter, which is negatively charged. And so now most of our dimethylamine is going to be free and not associated with organic matter. Again, we're adding coagulants as well. And so now if we click again, Bill, our NOM after softening is largely removed, like 50, 60+% of the organic matter ends up being coagulated and deposited to the bottom, settled out. And now if we add our chloramines to the water, now we have most of our precursors, in this case dimethylamine, as being free. And so it's going to be much more reactive and much more available to react with monochloramine. We have much more monochloramine around because it's not being consumed by the organic matter, and hence our yields of NDMA are going to be much greater after softening. Okay, so next slide. So summary and conclusions. So next quick. So NDMA precursors in the crow, I think I've demonstrated, were highly dynamic, but exhibited relatively little spatial variation. So we did not identify any hotspots which would point to a specific industry or activity that's a critical problem. It seems to be that the precursor concentrations are entering all along the river. However, there are quite varying concentrations over time, as I showed. The sources of precursors, according to our land use analysis, suggested that animal operations were the most important, followed by domestic wastewater, followed by croplands. I also showed you that NOM decreases NDMA formation by consuming chloramines and potentially by shielding precursors from reaction with those chloramines. And then lastly, I also showed you that the preferential removal of humic substances via softening, in particular those in region 5, the humic acids in particular, reduced NOM competition and resulted in an increase in NDMA precursor concentrations as measured by UFC. So that concludes the first part of the talk, and then Bill will talk about our non-target analysis work for precursor identification. So I'll turn it over to Bill and turn my mic off.
Thanks, Ray. And I'll pick up from there by saying if we go back to that removal within the excitation emission spectra, that we removed the humic and fulvic acids, but left behind the proteins and the microbial byproducts. And both of those things likely arise from either human or animal waste potentially, right? And so that means if we've got more runoff from agricultural operations or animal feeding lots or from wastewater treatment plants, there might be specific precursors in there that we could look for that might be driving the NDMA, and that's what we did here. So the first one we wanted to do is actually extract the potential precursors from the water samples. And we used something called a mixed bed cartridge where we used multiple solid phase extraction phases to try and get as many different types of compounds as we could out of the water. And this was developed by actually in Switzerland, but used a lot by a group at Cornell. And Jackie did some initial tests and found out that somewhere between a third and 90%, and the third was the outlier, were retained on this cartridge of the NDMA precursors. And so then we did detection and comparison in pre and post chloramination samples. And we used something called liquid chromatography, time of flight mass spectrometry, and did a sample comparison approach where we have a raw sample or a lime softened sample, both pre and post chloramination. And then we use this mass spectrometer and we get two spectra, one before chloramination and one after chloramination. And what we're looking for here is really samples that drop dramatically during chloramination, because those are compounds that are highly reactive and maybe potential NDMA precursors. So we look at this ratio of post-chloramination to pre-chloramination. We call that our chloramination degradation ratio, and you'll see this CDR multiple times. So we did this in the Crow River, and we actually just picked one spot, because this is a lot of data that comes from this instrument. And we did it weekly for 6 weeks to see if we got temporal variation. We didn't have time or bandwidth to do spatial variation for this. And we did raw samples, raw post-chloramination or post-ultimate formation conditions tests or universal formation conditions tests, and then the same before and after lime softening. So the workflow here is we look at all of the different features that are in the mass spectra, and this is something that the software does for you and tells you something that thinks there's a molecular formula that it can determine. And there were a total of 5,500 features. But then some of them we only detected once or twice or not very often. And so we narrowed that down to things we detected at least more than 8 times in all the samples we took. And then we looked for things that had a chloramination degradation ratio of at least 0.85, meaning at least 15% of the compound was reacted. That narrows it down to 242 features. And we did relax this a little bit. And then because we're looking for NDMA formation, we know we need an amine type of structure. And so the formula has to contain nitrogen. There are lots of other structures, phenols and the like, that will react with chloramines, but they won't form NDMA if they don't have nitrogen in them. So that gets us down to 220 features. And then we could subject some of those to MS2 analysis, which allows us to get some structural information about these molecules and then compare them to databases to see if we can find specific contaminants. And this chloramination degradation ratio, we see a range of values and versus number of detections. And we divide these up in different groups where we have this less than 0.85 and kind of met all of these things here. We identified of these 36 compounds, 20 of them, and 12 of them were known nitrosamine precursors. And those appear here. Group 2 is where we relax that assumption a little bit, where they might not be quite as reactive, but we did find 3 compounds and another nitrosamine precursor. Things that actually are disinfection byproducts, where they're actually the ratio is higher. We looked for a couple of those too to see what we could find. So we did find 15 nitrosamine precursors. We are limited in what we can find as to what is in the databases. And so that tends to be synthetic organic molecules that are used in pesticides or pharmaceuticals. right? And that's what most of these things here are. We found metformin, lidocaine, tramadol, venlafaxine, ranitidine, which we talked about before. Even though it's pulled from the market, people must still be using it. This compound here was interesting to us because it didn't seem to be a pharmaceutical itself, but it might be a degradation product of this antipsychotic medication. We also found these two kind of surfactant molecules, which are NDMA precursors. And then we'll say recreational compounds as well. So a nicotine degradation product, as well as cocaine, which has a low NDMA yield. Some of these molecules also are in the opioid family as well. And then also tributylamine, which is just a very common kind of anti-corrosion and industrial molecule as well. So for all of these compounds, we could look at the chloramination degradation ratio, and all of them have pretty strongly, and this is kind of the average over time for all of these, or all the samples of what the CDR was over all of them. And obviously the different water samples are going to have slightly different water chemistry each time we collect them. And so the amount they get to grade is going to be different depending on what the NOM was that week. But we can see all of these are pretty highly reactive. We can also see that in the raw and the lime softened water, there isn't a huge difference in the amount that's of the compounds. These are the amounts of compounds present, so they're not removed at all. And then the amount of NDMA form doesn't change that much, or the NDMA of UFC in these different water samples, because we're basically not removing the precursor compounds. Not that these are the only precursors, and in fact, they can't identify, this doesn't account for all the NDMA we see, because we can semi-quantify these. And the main ones we identified are pharmaceuticals for human use. This doesn't mean that the animal feedlots aren't contributing. It might just be molecules that aren't in the database. And we also see correlations between the amounts of these molecules present and the NDMA formed in the system. So it's not that these molecules are definitely driving the NDMA formation, but they're good indicators that there are more compounds in the system that could form NDMA under the chloramination conditions. And back to this map of all of these features, where we have this broad range of compounds, where we have CDRs that are highly reactive, are these red molecules with ones greater than 2. We broke down this broad range of 0.5 to less than 2, and I just did that backwards. The CDR, the highly reactive ones, are the 0.5, right? Where you have post-chloramination, you have lower levels than before. The greater than 2 are actually disinfection byproducts that are formed, because they have much more after chloramination than before. And you'll note here that we have a lot, this is plotted versus retention time on the HPLC. You notice we have a lot of these CDR less than 0.5 compounds that are out at the tail end here, which means they're pretty hydrophobic. And, but they still potentially would form NDMA, or they're highly reactive with chloramines. Now, these are probably larger molecules. They could be microbial byproducts, some kind of amines that we're excreting or that are processed from animal waste, but they're not necessarily pharmaceuticals or pesticides or the like. They still could be anthropogenic in origin, leading to NDMA formation. And then these high CDR molecules, or low molecular weight hydrophilic, they're disinfection byproducts that probably merit some future investigation as well. And because they have nitrogen in them, they're certainly nitrogenous DBPs, which means they could be nitrosamines. So we found a bunch of other anthropogenic compounds as well. These have nitrogen groups in them, and so they will react with chloramines. These are various pharmaceuticals and pesticides and pesticide degradation products. Gabapentin, very common pain medication. Carbamazepine is a very common psychoactive drug. Degradation product of atrazine. Atenolol here is Lipitor. So all of these compounds also are present in forming disinfection byproducts, but potentially not nitrosamines, or at least not NDMA. So now that we know that we have compounds that could form NDMA in the system, and that they tend to be reactive, at least they can be oxidized, and they're reacting with chloramines, we were investigating with our master student, Eric No, how we could control NDMA formation. And this was a collaboration with St. Paul Water. Because these compounds are oxidizable, potentially we could pre-treat with another oxidant before we chloraminate to degrade the nitrosamine precursors. And we did this both in the raw samples, the lime softened samples, and in the lime softened samples after they've been recarbonated. And so where you potentially would do this in the drinking water treatment chain. So like if you did it for the raw samples, it might be to destroy precursors and remove some iron, or do other oxidation that's necessary after lime softening. It would be more treatment case or recarbonated. So we can see in all these cases, no matter what oxidant we used, whether it was ozone, an AOP where we had ozone plus hydrogen peroxide, or free chlorine, which is only really relevant in the recarbonated system where we would do that, we really knock down the amount of NDMA that's formed in the system. And the reason we think we don't see a huge difference between the lime softening and the recarbonated is that probably most of the ozone in all of these cases is being converted to hydroxyl radical under the conditions we're doing this. We then actually spiked some water with ranitidine, which we know has a very high yield, and saw that even when we have that high yield compound in there, if we do various oxidative treatments, and this is like ridiculously high NDMA formation here, we can knock it down to, with ozone and free chlorine together, below that Minnesota notification level. And so it is possible with systems that are already present at drinking water treatment plants to control NDMA precursors. So for this part of the study, we've developed a useful tool to screen potential precursors, this chloramination degradation ratio that you can do using mass spectrometry methods. We did find 15 precursors, and we are limited by the databases and what's available in them. And Jackie spent a lot of time digging through various the databases that came with the instrument, as well as other online databases, trying to match spectra with known compounds. But the compounds we identify can't account for all the NDMA that we see. So there's many other chlorine main reactive compounds that are likely from human or agricultural activities. They may also be from natural compounds present as well that are leading to NDMA formation. And that's where this hydrophobic dissolved organic or natural organic matter comes in. But using pre-oxidation, we can control this formation at the drinking water treatment potentially, which would then minimize human exposures. And with that, we can take the remaining time for questions here. And I saw at least one pop up in the chat, but it flew by and I didn't see it. So.
All right, great. Thank you. Yes, we do have one question in the chat so far, and if there's any others, feel free to put them in the chat and we will get to them for as much time as we have left. So we do have a question here from Scott. Are there any lessons we can take from this research and apply to wastewater? Most wastewater that is chlorinated is very quickly chlorinated. Would a shorter chlorine exposure time make a difference?
I can start, Ray, since I'm unmuted. So I think with wastewater, you're going to have formation of some kind of nitrosamines when you chlorinate there, just because there's higher levels there. We were more interested in what was happening at the drinking water treatment plant system there. And I think unless you're doing direct potable reuse, probably the chlorination at wastewater isn't going to be a huge deal. There's some residual ammonia there. You will get some NDMA formation, but when it goes out into the environment, NDMA is actually degradable by sunlight and some other processes. And so hopefully by the time it gets to the drinking water treatment plant, the human exposure will be minimized and the environmental consequences should be, I think, I'll say relatively minimal, but Ray may disagree with me.
Yeah, and it might also depend on how well plants are nitrifying or let's say nitrifying the water. So most plants have pretty good nitrification efficiencies and very little ammonia when they add the chlorine in the water. So they shouldn't form a lot of NDMA typically in the wastewater. So it really depends on the effectiveness of their nitrification, how effective they are converting their ammonia to nitrate before they disinfect. And so Yeah, otherwise, if you're talking about trying to remove precursors in wastewater, yeah, I don't think the chlorine doses are going to be enough to really affect the precursor levels substantially.
Yeah, and unless you go to like the Swiss system where they ozonate all their wastewater to try to get rid of the emerging contaminants there. And I think some of the reason the NDMA issue arose in the first place is California looking at direct potable reuse, right? And so if you're taking wastewater, treating it and sending it to drinking water, then you have to really be concerned about NDMA and getting rid of all those precursors.
Yeah, I was really interested to see the precursors you came up with through your investigation, Bill. One of the things that I was curious to see was that metformin and phenylphexin tend to be kind of at the top of that list. We see a lot of that in surface water around the state. Those two chemicals usually are like in the top 20, top 10 to top 20 detections, what we see in surface water. And together with lamotrigine sometimes and carbamazepine, I think you know too. So
Yeah, we
it's
see
really
fluoxetine too.
Yeah, so it's really interesting to see the correlation there.
Yeah, and Jackie will correct me if I'm wrong too, but we did see some opioids, and then one of the structures, it's interesting because there's an opioid and something else, and they're the same exact same molecular formula, just the atoms are arranged differently.
Yeah, we know metformin is a type 2 diabetes med. It's very commonly used.
Yeah.
Yeah.
And yeah, gabapentin is another one that's super common as well.
There's another question here, Bill. Something about disposal of medications. You want to comment on that?
Yeah, and so I think medical practice has got much better in this respect. And so Mark, I know, is part of the One Health collaborative in Minnesota about antibiotic use, where we're looking at resistance and disposal and all things like that. And the Department of Health has done a very good job of advertising to medical professionals as well as to consumers so that they don't put your drugs down the toilet anymore. The issue, of course, is that a lot of the reasons we see these drugs is because we take them and we excrete them, right? And because the reason you have to take a drug every day is you're constantly flushing it from your body. And so we're never going to get rid of all of them from the environment unless we stop taking medications ourselves. But yeah, take back programs and things like that are important. And, I think it goes through cycles of when we have advertising budgets to talk about those things. But that's an important role here as well. And of course, for animals, that's a different ball of wax.
Great. Well, thank you. And we are at our end time here, so we'll go ahead and wrap things up. If anyone has any remaining questions for you two, I'm sure that they can reach out to you over email and connect with you if they have follow-up questions. But thank you so much for joining us today and sharing your work. We really appreciate you taking the time to share your expertise and your research with all of us to learn from.
Thank you.
Yeah, thanks so much.
Yeah, if you would like a copy of the papers, or let us know. We've published most of this work already in the journals, in the peer-reviewed literature. So, or any questions, please send us an email. Thanks.
Great. Thanks, everyone. Have a great day.
Bye-bye all.
Thanks so much.